Parfait. OK. On commence, Cédric? Okay, welcome everyone to this session, which is the second part of dynamical processes in the upper ocean related to surface current and dispersion. The morning session was chaired by our colleagues Greg Sutherland and Nancy Suntians, and my name is Danny Dumont, and I will co-chair this session with my colleague Cédric Chavannes, both at Université du Québec à Rimouski. So I remind that the presentations are 12-minute long with to leave 3 minutes for questions, ideally. So Cédric will notify you when you got 1 minute left. And you can continue, but that will go take some time into the questions. And note that in the agenda, after the third presentation, we have a 10-minute break. And I suggest that if there's time there, for questions that were not asked for the first presenters, we can take that opportunity there. So, and then we'll try to stay on time. Starting right now with the our first presenter, Guoqiang Liu.
Yes.
Guoqiang, you're ready. So, the floor is yours. Thank you.
Okay. Yeah. Okay. Today I would like to talk about the surface impacts on the momentum flux on the upper ocean current under storm track. So here, first I would like to talk about how the surface wave impact the ocean dynamics in the ocean wave current couple model. Typically, it can affect the general ocean circulation, near inertial motion, and upper ocean dynamics. And here, about the moment.
Are you able to put you in share screen mode, in display mode?
Oh, the better?
Excellent.
Okay.
Thank you.
Yeah. So about the momentum flux, actually I call it there is two parts. The first part is about, I call it the direct impacts. So the sea surface, sea state dependent surface at bottom roughness, and the surface wave growing and decaying on the momentum flux at the air-sea interface. And the second part I call it the indirect impact, is which I call it Coriolis Stokes force and vortex force, Langmuir turbulence, and the river breaking. This part can induce the momentum and energy flux from the wave to the ocean. If you look at this figure, so if you just, this paper is about 10 years ago, a paper by me and Will. And if we just consider the sea surface roughness, so we calculated the wind power to the ocean circulation. So this one is that the wind power to the ocean circulation with wave impact. So this one is the wind power to the ocean circulation without the surface wave roughness. So this is the term. This is the difference. We can find that actually without considering the surface wave roughness, it can cause 24% difference, and the maximum is found over the Southern Ocean, where they often correspond to the big waves in the non-equilibrium. So here I show you a figure about the passive LC, the momentum transfer. Actually, when the wind blowing over the ocean surface, and we have to calculate the wind stress. So here, tau A, we call it the air-set momentum flux. Usually, we using the surface following buoy to observe the wind fluctuation and get the we do the Reynolds average and get a CD and U10, and we get tau A. The tau A actually have 3 parts to the ocean current. The first one is it actually is going to the long wave of the energy containing bed. So causing this wave to grow with fetch while losing little momentum to the share is this part. Actually, this is the wind blowing over the existing waves generated from other regions, not the local generated surface waves. And the second part is the biggest part is called the short waves. Actually, we transfer their momentum through the braking to this part. These are local generated short waves, and the short waves immediately break, and the momentum energy goes to the upper ocean. And the third part is that actually the wind stress directly over the current with the viscous stress directly to the shear flow, actually the current. Most of the we calculate tau A. Actually, we using this buoy. We just calculate the tau A actually above the surface. It's called air set. Some engineers found that this body they measure the currents in the ocean part and calculate the water side momentum flux. And there were some other studies about this, but this one is the most famous one. So here I just show you the how we calculate this tau OC in the how can we present this size in the wave current coupling model. Actually, the momentum flux from the air side and the air side wind stress to the wave, we can calculate it in the wave model. This part, this tau in, which is transferred from the wind to wave, and the wave dissipation stress we call tau ds. Calculate this. So finally, the momentum flux to the ocean is the sum of the flux transferred by turbulence across LC interface tau A minus tau in. This part actually is this, the third one, that directly go to the current. So finally, we get a tau OC. This one is the real stress go to the ocean, not tau A. But usually, if we just ignore the wave impact, we will get tau OC equal tau A, which is not right. So graded effect of surface waves on tau OC in the mid-latitude West Atlantic, the Pacific, and the westerly the Southern Ocean, corresponding to the high inverse wave age and high wave here, the young wave. In the young wave, actually a lot of momentum fluctuation can store the wind momentum. So how big is the difference about the tau A and tau OC? Here I show you the example. So and I said that under the hurricanes and the strong wind events, we can see that this one means that tau A equal to tau OC. This is the center distance from the center. This is the center. So we can find that actually the tau OC, most of the tau OC is less than tau A. It means that the waves are green. It needs the momentum from the wind. So and this side tau OC less than tau A, and it's all like this, and it's up to 35%. So it's a big fraction. It's not small. So here I give an example. So the right now we have more temporal and spatial resolution to forcing the climate model. Previously we have monthly wind, weekly wind to forcing the CMIP5, but right now we have hourly wind. But if we're using hourly wind, we have to consider the wave impact because the hourly wind can resolve the hurricane, the storm, and under the hurricane storms, if we ignore the wave impact, we will put more momentum and energy to the ocean. So here I give an example. The momentum flux is the U10-2 power, and the energy flux is the U10-3. So here I give an example. If we have 20.5 meters per second a week, it equals 5.6 meters per second a year, the energy. So we have additional discussion. So evolving surface wave on the momentum flux over the fetch limited coastal areas essential for the coastal circulation also. So this part is issue that is very important. So here I give you an example about 1D processes about the storm case in the Atlantic Ocean. I use a wheel watch model to calculate tau A and tau OC here. This is the difference, and this is the inverse wave age. We found that the very young, the bigger, the younger of the waves. So the younger waves corresponding to the big difference of the tau A and tau OC. So we're using the tau O and tau OC forcing the SLA model. We found that the near initial current are very big difference. This is the U and the V, and this is the initial kinetic energy, and this is the integrated in the initial kinetic energy. This part is actually the 40%. It's a very big fraction here. So I using this SLA model to the global ocean, and I found that over the mid latitude and the southern ocean, without considering the wave impact, there is a big difference about the near initial current. We all know that the near initial current is very important. So for this 3D these processes here are using the idealized wave and ocean current couple model, and I calculated the tau A and tau OC, and forcing idealized typhoon. And here, this is the model distribution of wind directions and mean wave direction here. Okay, and this is the inverse wave age and the difference between tau A and tau OC. Look at it; it's big enough. It's up to 0.4 Newton per meter second. So here I'm using this tau A and tau OC and forcing the ROMs, and we found the difference here. So the A here actually vertical transect near initial current velocity calculated by tau A, and it's a difference compared to the one forced by tau OC. The solid and dashed lines represented by MID simulated by tau A and tau OC. This is the miscellaneous depths, and the impact of surface on the near initial current per and can.
Jokshan, you have 1 minute left.
Okay. So so here I'm using the Atlantic Ocean case. I forcing the whole this small region, and okay, I get to the result. So this is the difference of the tau A and tau OC actually, and this is the ratio, and we found that over this is the inverse wave age. The bigger, the younger the waves, we have a bigger of a difference. So this is important. And also we found that if the frequency are bigger, actually bigger than the initial, we have a big difference about tau A and tau OC. This is the difference about the frequency band. And over the, I calculate a location, and we found that this is the difference of tau A and tau OC. We found the difference. This is stop, and the kinetic. We calculated the kinetic energy from the ROMs. This is the difference of the from 2 ROMs simulation, and this is the this is WPI as the actually wind power input. So we can find the big difference if we consider the wave impact. So here also we found that the effect of surface on the ocean current velocity is different frequency. The near initial region, the right line here, and greater than the 1.2 initial frequency region, the blue line, less than the initial point. We call it the circulation. So this part actually is the biggest, is up to 20%. It means that the bigger of the frequency, the bigger of the wave impacts on the current. Thank you. Okay, thank you. This part is too long. Thank you. and you can download all of my code from my research git about the Stoker drift and the wind stress and towing topsy. Thank you.
Thanks, Go-chan. We actually have maybe a time for one short question. Jinyu?
Yeah, thank you, Danny. Go-chan, in calculating the wind stress to the ocean, should we consider the effect of surface ocean currents? What I mean, let's say you have a wind, let's say 10 meters per second. My surface currents also, let's say 2 meters per second, let's say I assume, okay?
Yeah.
So should we consider relative velocity in the same direction, assume, right? So in calculating the tau A.
Yeah.
Okay, we should consider the relative wind effect, right?
Yes, of course,
Okay.
yeah.
Okay,
Actually, we have.
Yeah.
Thank you.
Good. Okay, good. Yeah. Thank you. Good talk.
Thank you.
That was a really clear answer to a clear question. Thank you, both of you.
Thank you.
Really interesting, Go-chan. So our next speaker now, and maybe we'll have time for some other questions, Go-chan, later, is Jin Tao. Is Jin there? Everything's supposed to be tested. Yes. Thanks.
It's good. Yeah. Good afternoon, everyone. My name is Jin Tao. I work as a research scientist at BIO. First, I would like to acknowledge my co-author, Hui, Rick, and Will. Today, I would like to present our work entitled Autometric Index of North Atlantic right whale habitat in the Western Gulf of St. Lawrence. The ocean circulation is an ecosystem driver that affects water mass, nutrient, and the spatial distribution of whales. Relevant oceanic conditions such as oceanfront eddies, which are important in the zooplankton aggregation. The satellite altimetry with higher spatial and temporal resolution has been applied to study sea level and the surface current variability. Application of altimetry to investigate the connection between the physical driver and the zooplankton prey related to the presence of whale have not been made. In recent years, the Gulf of St. Lawrence has become recognized as the North Atlantic right whale aggregation area and feeding ground from spring to fall. Sightings of the North Atlantic right whale have been frequent in the southern Gulf of St. Lawrence, especially in the Shardik Valley. The pink dot here are the whale sightings during 2015 to 2019. In the Gulf of St. Lawrence, large amount of the fresh water enters the Gulf from the St. Lawrence River. The buoyancy forcing and the tidal forcing are known to impact the Gulf of St. Lawrence system. The notable features of near-surface circulation are the Gatsby current and the anti-acoustic jar. The strength of the Gatsby current and the anti-acoustic jar are determined in part by the fresh water outflow from estuary and the westward flow along the north shore of the Gulf. The Gatsby current is a freshwater pathway to the southern Gulf of St. Lawrence, providing the canals from St. Lawrence estuary. As the physical driver of the zooplankton supply to the southern Gulf of St. Lawrence, the strength of the Gatsby current can be considered a potential predictor of the North Atlantic right whale habitat suitability. The goal of this research is to develop physical index using satellite altimetry observation to monitor physical process in the northwest Gulf of St. Lawrence and detect variation in whale habitat suitability. There are two objectives. First, develop an index parameter to characterize the Gatsby current intensity. Second, explore the correlation between physical index and zooplankton variables to predict spatial extent of the whale habitat in southern Gulf of St. Lawrence. Next, we show the data we used. The monthly mean estimate of freshwater discharge at the head of St. Lawrence estuary were collected from 2009 to 2021. The highest monthly mean runoff of the year is typically in April or May. The bottom panel here shows the time series of the accumulated runoff from April to September. And here we found the accumulated runoff are relatively higher in 2011, 2017, and the 19. Next, the Bless et al. 2021 provide the detailed summaries of the zooplankton variation at Shattuck Valley Station. The figure here shows the temporal variation in normalized annual anomaly of 6 different zooplankton index, which includes the total zooplankton biomass, warm water, cold water associated cohort. The Galanos fin markers is a major component of the North Atlantic right whale dive. And the Galanos hyperbolis and the pseudo-Galanos are also potential prey. Next, here shows the North Atlantic right whale sighting pattern from 2016 to 2019. The different samples correspond to whale sightings observed in the different months. Here, the whale sightings were more concentrated around the Shattuck Valley in 2008 and more widely scattered to the south and the east in 2017 and 19. We should care for that. The sighting data may be biased to the area and the time. The satellite altimetry data used in this study are taken from the CMOS. Here, our work used a smoothed sea level anomaly product with 7 km and a 9.9 day resolution. The JSON ground track indicated as the black line here, which will cross the Gatsby current and the anti-acoustic jar. Here is an example of the SLA profiles. The y-axis is the latitude. The whales are sighted most frequently between the May to October. So we collect the SLA data during those 6 months. The physical index are derived from the SLA profiles. We define the slope of the SLA along the track as a measure of the geotraffic current intensity. The index slope is calculated using a linear fit of SLA profile along the entire track, and the index slope half using the southern half of the JSON SLA profile. Note that the positive index slope half indicates the westward current, and the negative slope value indicates eastward current. The third index is given by the gradient between the maximum and the minimum value of SLA along the track. An indexed volume transport through the track also calculated using this equation. Then we move to the result. The figure here shows the time series of the index slope half, which shows the interannual variation. The dots are colored by months. In this box plot, we found the mean value of the index slope half were low in 2013, 17, and 19. During the 2015 to 2019, the mean value of index seemed negatively correlated with the river discharge. The previous study indicates that a seasonal increase in the St. Lawrence River discharge typically results in a strengthening of the Gatsby current. And here is the monthly variation of the index. The lower value were observed in May, June, and July. The higher value were observed in August and September, which is consistent with the river discharge variation. Those results indicate the slope index inversely proportional to the intensity of Gatsby current. Let's move to another 3 index. The indexed slope full and the indexed gradient provide a complementary characterization of the physical process in the northwest Gulf St. Lawrence. There are several dynamic processes, such as the eastward Gatsby current, the biotropic west jet along the north shore, and the anti-acoustic jar. The index slope flow is a measure of the overall cross-section surface water circulation, while the indexed gradient is a measure of the surface water velocity across the jar circulation. The indexed volume is a proxy for variation of the volume transport through the cross-section. Here it shows the time series of the indexed volume, which we found the time series shows a general upward trend from the 2015, and they got the peak in 2021. The one possible explanation is that the transport due to the biotropic west jet may increase during those years. The further study are required to test this hypothesis. Next, here is the correlation analysis among the discharge, physical index, and the zooplankton index using the annual mean. There are no significant correlation. P-value larger than 0.2 are removed. The value of the index slope of half and the index gradient show negative correlation with river runoff. It indicates that the index slope capture the driving force of the Gatsby current due to the upstream river runoff. Although our physical index are sometimes correlated with the zooplankton index at Shattuck Valley, but none of the six.
You are Jing, sorry, you have 1 minute left.
Okay, but none of the six indexed are significantly correlated with the discharge. This may indicate the performance of an automatic index is likely better than single variable like river discharge as an indicator for some zooplankton variation during this period. Last, we acknowledge that the variation in zooplankton abundance in the Shattuck Valley cannot predict solely from physical transport process. Here, our project is focused more on the physical control. Previous study found that the Gatsby current plays an important role in advection and the horizontal distribution of the calurnus in the southern Gulf St. Lawrence. An index designed to monitor the variation in Gatsby current may also be used as a proxy for the North Atlantic right whale prey and therefore a predict of whale habitat suitability. We found the variation of the index slope half seems broadly consistent with variation in the North Atlantic whale distribution during the 2017 to 2019. Here we found the index slope half values are low in 2017, 19, then the 18, which indicates that the Gatsby current intensity are stronger in 17 and 19. There are also differences in the North Atlantic right whale distribution during those 3 years. The whale sightings were more concentrated around the Shattuck Valley in 2008 and more scattered in the 17 and the 19. At last, the indexed slope half is shown to provide an estimate of a Gatsby current intensity. Automatic indexed are useful for inferring the ocean circulation features in the whale habitat ecosystem and can potentially be used as an indicator of zooplankton abundance transport in the Shattuck Valley. The satellite altimetry provide a unique tool for understanding and potentially monitoring of whale habitat suitability. And last, tomorrow afternoon, our group has another talk given by the Rick Danielson, which is focused on the ocean feature extraction from the SAR. At last, I would like to acknowledge our colleague, data source and funding agencies support this work. Thank you for listening. I'm happy to take the question.
Thank you, Jin, for this nice presentation. We actually have one question in the chat asked by Coach Han. Do you want to ask it, or so it says there?
Okay, I can ask.
Yep.
Yeah, I think it's a very nice use of satellite altimetry, you know, for the work, you know. And just curious, you know, the track you are using is a descending track, and it's not so aligned well with the, I mean, the gas speed current, I would say. But there's probably an ascending track approximately perpendicular to gas speed current. I'm wondering why you don't choose that one, you know, and instead of using the one now you used, you know.
Okay. Yes, actually, earlier of this project, we tested different satellite altimetry data, and we found the JSON 2 is and 3 cross the Northwest Gulf St. Lawrence, and they have a relative higher temporal resolution, like around 10 days. And so that's why we choose this track. They also have another track, but they not that good as this one. They clear cross the gas speed current and almost the middle of the anti-acoustic jar.
Okay, thanks.
Thank you.
Thank you, Jin. I encourage everyone to ask questions in the chat so that Jin can answer as well there, while we proceed to the next presentation, which is a recorded video that we'll try to share. And if it doesn't work, then Cedric will present it. So share screen. It's supposed to be it. Let's go.
I'm like a PhD student with Institut des Sciences de la Mer de Rimouski in Quebec, Canada. And today I'm going to talk about a new method to estimate the stuck drift based on wind field retrieved by single high frequency radar. So high frequency radars measure ocean surface currents by sending electromagnetic waves in the HF radio band and recording the electromagnetic waves backscattered by ocean surface gravity waves. The recorded signal is dominated by electromagnetic waves backscattered from ocean surface waves with half the electromagnetic wavelength called Bragg waves. Any surface movement in the direction of the backscattered signal produces a Doppler shift in the frequency of the received waves. In the absence of Miller-Lorentz currents and surface gravity waves, other than the Bragg waves, the backscattered electromagnetic waves are Doppler shifted by the linear phase velocity of the Bragg wave C0. In the presence of Miller-Lorentz currents, the phase velocity of the latter differs from C0 by these quantities, causing an additional frequency shift. However, a wave field is composed of several spectral and directional components. By nonlinear processes, these components can interact and affect the phase velocity of the Bragg waves. Stuck drift is an example of nonlinear processes which can affect the velocity of the Bragg waves. Since both Miller-Lorentz currents and surface gravity waves can affect the phase velocity of the Bragg waves, the question arises as to whether HF radars measure a quantity related to the wave-induced drift in addition to Miller-Lorentz currents. However, the literature is inconsistent on the existence and the form of the quantity related to the wave-induced drift. There are several options for the stuck drift contributions. So Laws and al. Propose these expressions where this is a wave spectrum and this is a Bragg wave number and this is a wave frequency. In other words, HF radar measures the stuck drift in the same way as they measure Miller-Lorentz currents. So here we have the second proposition formulated by Longuet-Higgins and Felix, the propositions formulated by Langenstein, namely half of the surface duct drift. These different expressions are simplified because they are expressed in terms of an unidirectional spectrum. By using the full directional spectrum, these expressions are more complex, and in our work, we use the full expressions. Finally, certain authors suggest that HF radar measure tolerance, and here is the study area. The study area is located in the Lower St. Lawrence estuary in Quebec, Canada. And there are two types of HF radar, two WERA at Pointe-à-Boisvert and Pointe-aux-Outardes, and two CODER at Pointe-au-Père and Sainte-Flavie. So to estimate the different duct drift contributions, we use a direction wave spectrum calculated with the acoustic wave and current, a WAC. Also, we use mean Lorentz surface currents obtained with all a wax. So since HF radar measures the weighted depth averaged LRN currents, we extrapolate the LRN currents measured by the wax to the sea surface, assuming linear Ekman dynamics to perform the weighted depth averaging. So we obtain improved correlations between the radial currents measured by the HF radars and the WAC currents extrapolated at the sea surface, confirming that the radars measure the currents near the surface. So here we have the comparisons between a WAC at Forestville and HF radar at Pointe-au-Père. And after adding the different wave-induced quantity to the LRN currents measured by the awakes, correlation significantly increased. The highest correlation is obtained using half of the surface duct drift, suggesting that HF radars measure the latter in addition to mean LRN currents. So now I would like to show this figure where here there are the temporal variations of wind speed and wind direction at the meteorological stations in the big channel industry area. And here we have the temporal variations of half of the surface duct drift that have been obtained with the WAC at Forestville and the LRN currents for the same WAC. And here we have the temporal variations of the currents measured by HF radar at Pointe-au-Père and the LRN currents of a WAC at Forestville after adding half of the surface duct drift. These results show that HF radar measure half of the surface duct drift in addition to mean LRN currents. So this result has some practical application. For example, half of the surface duct drift should be subtracted from the HF radar measurements of surface currents before assimilating such measurements into purely LRN ocean numerical models. So we need to estimate the surface duct drift at any point on the grid covering the geographical area of interest. So to estimate the surface duct drift, we need wave spectra. Wave spectra can be obtained from HF radar. This method are based on the echo Doppler spectra of sea wave, more particularly using the second order echo, but is sensitive to the determination of the second order echo Doppler frequency, which could be difficult. So here we propose to estimate the wave spectra with a theoretical wave spectrum, which is the formulations of Toba spectrum. This Toba spectrum is a function of frequency, fetch, and wind field. If we know the wind field at any point on the radar grid, we can estimate at any point on the grid a spectrum and finally the Stokes drift. So I think you understood by now that we are trying to answer these questions, how to estimate Stokes drift with single HF radar. So to answer this question, we propose 3 steps. The first step is to estimate the wind direction with single HF radar. And the second step is to estimate the wind direction at any point on the grid with single HF radar. And finally, with the wind field, we can estimate the Stokes drift. So now we are going to estimate the wind direction. So the 2-dimensional distributions of surface wave energy in a kilogram, where the wind can be modeled as a coordinate distributions as a functions of angle with respect to the wind direction. So positive Bragg peaks in this spectra are associated with waves approaching in the radar seat, whereas negative Bragg peaks are associated with waves receding from the radar seat. The relative height of the two bragg peaks contains information on the wind direction. For example, if waves propagating towards the radar are much stronger than waves propagating away from the radar, then the bragg ratio is large and positive, and the wind is assumed to be directed toward the radar. The opposite conditions occurs when the wind is directed away from the radar. However, there is a left and right ambiguity for the wind direction. Traditionally, to resolve this ambiguity, estimates from a certain radar set that observes the ocean from a different angle are used. So here we propose a new method to solve this ambiguity with single HF radar. We assume that the wave does not change direction much over the observed area. Here we have the representations of each solutions. So the left or the right solutions in our study area. Here we have the histograms of each. And to solve this ambiguity, we concatenate the two solution matrices. Here we have the histogram of the concatenated matrix. From this histogram, we take the model wind directions of the study area, and then for each grid point, we study the difference between the left or right solutions and the modal directions, and we keep the solution for which the difference is smaller. So now, to estimate the wind speed, we decompose the surface currents of HF radar in three components, namely the steady currents, mainly refers to the geostrophic currents, the tides, and the wind-driven HF radar. Then wind speed is obtained by creating an empirical relationship between in-situ wind speed and wind-driven HF radar currents using an artificial neural network. We use this neural network within inputs, the radial currents of HF radar and the wind directions obtained with HF radar. So after estimating the wind field from the radar, we can estimate the TOBA spectra at each grid point to finally obtain half of the surface drift. So to conclude, I would like to show you this figure. It shows different steps of our methods, namely estimation of wind directions, where here we have the temporal variation of the wind directions obtained with HF radar in red, and the temporal variations of the wind direction measured at the buoy in black. And in the similar way, we have the temporal variations of the wind speed. And here we have the temporal variations of half the surface drift obtained with HF radar in red, and the temporal variations of half of the surface drift obtained with the WAC. And to end my presentations, I would like to show two big results, namely a map of the wind field obtained with HF radar in the lower St. Lawrence estuary in Quebec, Canada. So the blue arrows represent the wind field estimated with this radar, and the red arrows represent the wind field estimated with this radar, and the black arrows represent a reanalysis data set for our area. And now a map of half of the surface drift obtained with HF radar in the lower St. Lawrence estuary. So to conclude, I would like to emphasize this important result, namely HF radar measures half of the surface drift in addition to mineral currents, and it is possible to estimate the wind field with single HF radar, and finally we can estimate surface drift with single HF radar. These results have some practical applications. One is that half of the surface drift could be added to the HF radar measurements of surface currents to account for the full surface drift in applications for which the surface drift is of interest, such as oil spill tracking. Conversely, half of the surface drift could be subtracted from the HF radar measurements of surface currents before assimilating such measurement into purely layer and ocean numerical models. So thank you for your attention.
Thank you, and sorry for sound interference during the talk. Are there any questions that you can ask Cedric about what has been presented by Abigail? And we also have a few minutes more, actually 10 minutes before the next talk, if you have questions for a previous presenter as well. So I guess I might ask you one question, Cédric. Does this method work for any type of radar? Either.
Oh, you mean Vera versus Codar?
Yeah.
Yes, we've tried it on the Codars as well, and we can retrieve the wind field, but in very specific conditions. The difference between the Vera and the Codars is that the Vera is steering like we do an artificial beam steering with our receive antennas. And so we look at a particular direction over the sea surface. So we can have the full Doppler spectrum at every grid point of the radar coverage and compare the magnitude of the two Bragg peaks, which is needed for the wind field. So we can have the wind field over the whole domain. In contrast, the Codar has a single antenna with 3 elements and is using a different method to retrieve the direction of the signal. And this method is using each Bragg peak separately. So in order to retrieve the wind field for a particular location, you must have an output from the 2 peaks at the same location, which doesn't happen quite often. So you end up having a wind field which is very sparsely populated. And so it's more difficult to use our method with Codars. Also, it would work at certain grid points of the coverage.
Great, thanks. So if there are no other questions,
I have a question for Jing. Jing.
Hi.
Hi. So the along track altimetry data you are using, you said had a 7 kilometer resolution.
Yes, it's a 7 kilometer spatial resolution.
And I know that the width of the gas peak current is quite narrow. It's around maybe 20 kilometer, which means that you'll have at most 3 grid points over it. So I was wondering how good it is to resolve the strength of the gas peak current. Have you compared with some actual observations of the current?
Actually, I will assume the gas peak current also affects a little further. So we track the gradient of the sea level anomaly to understand the strength, the intensity of the gas peak current here. But unfortunately, we don't have like the institute data to compare with the satellite altimetry observation.
Okay, would be interesting. Maybe if you can find such observations, or maybe that would be for a future experiment to do.
Yeah. Yeah, thank you for your question.
Thank you. Are there any other questions?
Yeah, go ahead, Jinyu.
Hi, Danny. I have a question for Jing, and also Jing. I wonder, suppose you have a 3D model result of a circulation in the Gulf Slurs.
Yes.
Is it possible you can use your methodology based on the 3D model result to verify your index? The strength of the gas peak current and variability. That's my real question.
Yeah, that's a good question. Actually, in our manuscript, we already discussed that we could use a model to examine the correlation between the index and the gas peak current transport. But here, I think we would like to provide some observation to compare with the model. Maybe they can help give some give some help to support their model result. But we definitely like to compare with the model result.
Yeah, excellent. I'm kind of looking forward to reading your paper. Yeah, excellent.
Thank you.
Yeah, good, Jing.
questions. So the next presentation will be at in 5 minutes with Colin. We'll just see you around.
Should I go ahead and share my screen, or is it a little early?
I think you can start sharing, but we'll wait until 50 before we start.
Okay, can you hear me, or am I a little too quiet? Okay.
No, it's perfect.
So you'll let me know when I need to start. I know it's a little early here.
Okay.
Are you able to put that in the presentation mode, Colin?
Yep.
Yeah, excellent. Look forward to hear that. Will is coming back.
All right, welcome back, everybody. So we will start again the presentations. with Colin Hughes about the effect of surface gravity waves on the upper ocean circulation and hydrography over the northwestern Atlantic during Hurricane Arthur.
Okay, thank you for coming to my presentation. I'd like to acknowledge at least my sources of funding, as well as Digital Research at Canada and Shared Services Canada for providing computers for me to run my model on. So just a brief outline, I'm going to go through an introduction behind some of my research, followed by the model setup and forcing, and then some preliminary results and conclusions. So the main objective of my study is to look at different wave effects on the upper ocean dynamics, most specifically Langmuir turbulence, wave breaking, and conservative Stokes drift impacts. And they would be the resolved scale vortex force, Coriolis-Stokes forcing, as well as the Stokes drift advection of tracers. I chose to look at Hurricane Arthur. And to do this, I'm using the coupled wave circulation model Quest. But the circulation component is ROMS, Regional Ocean Modeling System, and the wave model component is SWAN, simulating waves near shore. So just to briefly explain, Langmuir Circulation, I don't know if you can see my mouse here, refers to counter-rotating vortices in the upper wind mix layer, and it's generated due to the interaction between the Stokes drift and the current vorticity. This is known as the Craig-Leibowitz vortex force. If, for example, your model is of the fine enough spatial resolution to resolve it. The vortices tend to be on the order of 10 to 100 meters as the dominant length scale, so it has to be very fine in order to resolve it. So what happens is the Craig-Leibowitz vortex force generates regions of surface convergence, and that's where you get downwelling. And then you also have regions of surface divergence, and that's where the return upwelling flow is. You can actually see evidence of Langmuir turbulence with different debris that gathers along the regions of convergence, and these are known as windrows. And these streaks tend to appear largely in the direction of the wind. Now, of course, unlike this very nice little diagram from Leibowitz, the counter-rotating vortices are not perfectly symmetrical like this. They're actually highly variant both spatially and temporally. And that's why the phenomenon is generally referred to as Langmuir turbulence. So the circulation model that I'm working with, ROMS, solves the Reynolds averaged Navier-Stokes equation, which looks like this prior to the inclusion of wave effects. Then there's the Coriolis Stokes forcing, so it's the interaction of the Stokes drift with the inertial frequency. The non-conservative wave effects, so this is the wave breaking driven current components. There's the vortex force over the resolvable scale. So here, if your grid is too coarse to resolve Langmuir turbulence, you drop the Craig-Leibowitz part off and just refer to it as the resolved scale vortex force. And also the modification to the pressure known as the Bernoulli head. And that's just to maintain the incompressible condition when you're accounting for waves. So where's the Langmuir turbulence come in? Well, that's within the Reynolds stress. So the Reynolds stress is the turbulent mixing that doesn't get directly resolved by the model. It gets parameterized within a mixing scheme. And by including Langmuir turbulence within the mixing scheme, I end up modifying the eddy viscosity, which thus enhances the vertical mixing. So I selected Hurricane Arthur in 2014 because it came up along the eastern US seaboard and also impacted Atlantic Canada. And at its peak, it reached category 2, and it actually briefly made landfall in North Carolina. And it was the earliest hurricane ever recorded to have made landfall in North Carolina. And there it caused a storm surge up to about 4.5 feet before it later continued northeast and weakened. And it was actually an extratropical cyclone by the time it impacted Atlantic Canada, and yet it still caused a lot of tree damage and power outages. So up to 290,000 estimated houses and businesses lost power in Atlantic Canada, 144,000 of which were in Nova Scotia. And an estimated $12.6 million worth of damage in New Brunswick. So despite the fact it was extratropical, it was still quite a threat. So in order to investigate this with the coupled model, I have to generate initial conditions as well as forcing. So the initial conditions that I did were based on glories, and the boundary conditions were as well. So it was the glories reanalysis with a 12th degree resolution. And I also, to further enhance the position of the Gulf Stream, I included a sponge layer based on glories in all three of my open boundaries. Now, my domain is 1/18th degree resolution with 40 different vertical sigma levels. And also the wave model component included open boundaries where I used global WaveWatch 3 partition spectral data to allow waves from outside my domain to flow into it. Now the wind, I ended up using the large-scale ECMWF ERA 5 wind as my background wind. However, this is very coarse. It's about a 1/4 degree resolution. So it's not able to resolve the structure of the hurricane. So that's why I had to blend the RMS H wind, which is very fine resolution, with ERA 5 background wind. And I did so following methodology from Fan et al. 2009. Now, I did also include tidal inputs. That was from TPXO version, I think it was 9. So that's included within my model as well. Now, to just give a brief flavor of some of my results here, I'm showing some short animations of the significant wave height in the top left corner, the sea surface temperature in the bottom left, the surface elevation on the right, and the sea surface salinity in the bottom right. And the significant wave height grew to over 13 meters, despite the fact it only reached category 2 in strength. You'll notice it tends to be also larger to the right of the storm center than to the left, due to the wind forcing and the translation direction of the hurricane being the same, being consistent there versus when they're working against each other to the left of the storm track. And with the sea surface temperature, you also see enhanced cooling due to the wind forcing and also wave effects in the model. And with the elevation, you can see not only large scale changes, but especially the tidal effects here in the Bay of Fundy. So while I'm considering doing 8 different sensitivity experiments, here I'm only going to focus on a handful of them. So there's the fully coupled experiments. That's where I include all the wave effects that I've considered at this point. So the conservative Stokes drift impacts, that's the resolved scale vortex force, Coriolis-Stokes forcing, and also the Stokes drift advection of the tracers. Now the wave breaking has actually 2 different impacts. So the one is as a surface flux of turbulent kinetic energy, so that's within the vertical mixing scheme as a surface boundary condition. And the other is the wave breaking driven current. The Langmuir turbulence I've enabled, or I've coded and included within my model following Kanta-Claes in 2004. And then also there are not only wave effects on currents, but current effects on waves included within the model. So the circulation only or baseline case is run with no wave effects whatsoever. It's ROMS by itself. Then there's, the no wave breaking case, where I include all of the wave effects except for the wave breaking contributions within the circulation model. There is still wave breaking within SWAN in this case. And then finally, the no Langmuir turbulence test, where I include all the wave effects except for Langmuir turbulence. So to see if the model is working at all and producing reasonable results besides just if they look reasonable, one thing that I'm doing to try to validate it is to compare the sea surface temperature from my simulations with a satellite SST. So this is from the remote sensing system. It's a daily average from July 5th. And this final point is the midway point of where it was on July 5th. So at 12 hours UTC. Middle is the sea surface temperature daily average from July 5th from the circulation only experiment. And on the right, the daily average of the SST from the fully coupled experiment. Now below, what I'm showing are a couple of differences. So this is the circulation only with the blended wind minus circulation only with just the background ERA 5 wind. What you see is greater cooling, especially right along the storm track, predominantly to the right of the storm track. In the blended wind case, as opposed to just the background wind case. And there's also some warming a little farther to both sides. So what's happening here is the enhanced wind forcing is generating greater vertical mixing or vertical turbulent mixing, and also a greater divergence of surface currents, which is leading to more upwelling. So that's why there's more cooling along the track, and then the advection or enhanced advection is making the sea surface temperature a little warmer to both sides. And then the final little panel here shows the difference in the sea surface temperature between the fully coupled case and the circulation only. And this tends to be very large, can exceed 2 degrees. And it's predominantly not only along the storm track, but also in shallower water regions. Now remember, it's not just the circulation model as the open boundary conditions, but the wave model as well. So the Stokes drift can also come from outside mode domain into it. And a couple additional comparisons that I have here are between the fully coupled experiment and no Langmuir turbulence, and fully coupled minus no wave breaking. So in both cases, the cooling is not as strong as it is in the combined case, but you'll notice with Langmuir turbulence, it tends to produce cooling, not just along the storm track and shallow regions everywhere. There is this one little anomaly here, which that could be numerical noise. It's also in a very shallow water region, so I'll have to investigate that further. Whereas fully coupled minus no wave breaking would make sense for there to potentially be a little bit of warming due to the modifications of the advection due to the wave breaking driven current. And I also looked briefly here at the sea surface salinity. So the satellite data for the sea surface salinity, rather than being daily averaged, was weekly average. So I just selected July 1st to 8th to cover the main period of interest. And on the left here is the sea surface salinity from the satellite data. In the middle, from the fully coupled experiment. And then on the right, the difference between the fully coupled and circulation only. So you tend to see pretty overwhelmingly, although not universally, an enhancement of the sea surface salinity and fully coupled relative to circulation only. So what's happening is predominantly—
Colin, you have 1 minute left.
Okay. Predominantly, the wave effects are enhancing vertical mixing, again, both the turbulent mixing as well as the divergence of surface currents and resulting upwelling. This is bringing colder, saltier water up to the surface. And then last but not least, I'll show you results of a couple different buoy locations here that are just to the right of the storm track. So here, the red X's are the observations. The green line is the wave-only simulation. And the other 3 are the coupled experiments that I focused on so far. And you'll notice at this buoy, the wave-only experiment overestimates the peak. And while the coupled experiments are not perfect, they do a little better job representing maximum wave height here. And same thing at this other buoy, for NDBC buoy 41025. Okay. So the main takeaways from my research here so far, this preliminary results, are that both Langmuir turbulence and wave breaking have a noticeable impact on sea surface temperature. The combined effect was larger than each one individually, most prominent along not only high winds, but in shallower waters, so mostly along the continental shelves. So enhanced surface cooling, and in some cases over 2 degrees along the storm track. And this is due to predominantly the enhanced vertical turbulent mixing, but also again, the 3D effect. We have the upwelling due to the greater divergence of the surface currents. So in the future, what I'd like to do are not just a few additional validations, but I have some more modifications that I want to make to the model. Just as Go Chang mentioned earlier, there would be using the waterside stress to drive the coupled model. So there, instead of just assuming the stress driving the currents is equal to the wind stress, I'd be accounting for the waves. So there's the input from the wind to the waves, and then also the stress due to the wave breaking. So this would replace the wave breaking driven currents. I'd like to thank my supervisors, our research group, and sponsors. And if I have time, I guess, take any questions. And I guess I can stop sharing.
Thank you. Yes, we have time for a quick question. Greg?
Hi, yes, thank you for the very nice talk. Forgive me if I missed it. I was a bit curious how you calculated the air-sea fluxes in your model, like the turbulent fluxes.
Oh, yeah.
And was the wave breaking parameterized directly from the wave model, or did you use like a wind-based parameterization?
So the wave breaking is coming, yes, directly from the wave model. And the air-sea fluxes are within the bulk flux subroutines that's following ferroleol, and the input for that is from the ERA5 reanalysis.
Okay, thank you.
Thank you. We have to move on to the next speaker, who is Mohamed Ahmed, talking about variability of oxygen saturation in the subsurface waters of the Northwest Pacific from Argo oxygen data.
Yeah, I'm muting myself. Okay, thanks again. Do you guys see my screen? Good way? Yeah, good. So, hi everyone, my name is Mohammed. I'm working as a postdoc with Roberta Ham at University of Victoria, and I'm gonna do a little bit shift from the previous great presentations that presented in this session. I'm gonna talk about the variability of oxygen saturation in the subsurface water of the Northwest Pacific from Argo oxygen data. So I will start, basically we're giving you the take home message here. So I'm hoping by the end of this presentation, I convince you with these two main points. The first one, that actually Argo floats play a key role and can improve our estimates of the oxygen content and the extent of surface ocean disequilibria during the deep convection. And this is because Argo floats actually give us expanding our observation in space and time, especially during the wintertime convection, when we have lack of observations. And also it gives us more insights about the interannual variability of the convection and how it's actually the oxygen concentration is changing over time, especially during this newly formed water events. The second point, that newly formed water in the Northwest Pacific showed significant decrease or degree of undersaturation in oxygen. It's estimated around -2% to -8% at the end of the convection. So briefly here, if you're not familiar with Argo floats, so the Argo floats are autonomous instruments and carrying different sensors in port. And usually the floats are drifting around 1,000 meters for 10 days. And then it's actually sinking to 10,000 meters and rising back to the surface after that. And when it's actually going ascending up to the surface, start collecting in situ measurements for different variables based on the sensors inboard, as temperature, salinity, and oxygen, etc. And repeating these cycles every 5 to 10 days, and keep doing this for the float's lifetime, which is usually around 4 to 5 years. And this picture here showing you how the floats, when it actually at the surface, start sending this data over to satellites. And so we have kind of like near real-time data coming from the floats. So we know globally the ocean actually lost around 2% of the dissolved oxygen since 1950, or the last 5 to 6 decades. And actually it's predicted to losing 3 to 4% by the end of this century. And the majority of this loss mainly happening in the upper 1,000 meters of the ocean, which you all know, this is the regions that actually reach and have abundance of species. So in the left here, I'm showing you a slide showing you the change over time for the full water column. And if you can see red, that means it's actually there is decline, and white here means there is minor or no change in the oxygen concentration, and blue it means it's actually increasing. So you can see all over, or it's kind of like, especially in the North Pacific, there is a decline happening there. And if you look at the 100 meter for the 5 decades, you can also, there is a big decline in the oxygen concentration happening in the North Pacific. So you can see the North Pacific actually showing one of these kind of like secular trends of declining in the oxygen. And this is mainly happening for two reasons. The first one, which is quite obvious, the ocean is warming, and this is driving deoxygenation. So warmer ocean, meaning you have holding less oxygen in the water, and also warming the ocean causing stratification that actually can cause this separation between the surface and the deep water, and which is naturally have like less oxygen compared to the surface. And the second one is this excessive growth of algae, especially in the coastal area, due to fertilizer runoff and human impact. And this is causing also kind of decline or hypoxia in the coastal ocean. looking at how our ocean actually breathing in and out CO2 and oxygen. So this is the fluxes of CO2, and this is the fluxes of oxygen. This is, so here blue is meaning the ocean is actually uptaking CO2 from the atmosphere, and red does means the ocean is actually releasing. And the same for oxygen here, purple is meaning uptaking, and green is meaning is outgassing. And again, if you're focusing in the Northwest Pacific, you can see it's one of the few regions in our region actually that's showing the largest uptake of CO2 and oxygen. However, if you look at the projections of our oxygen fluxes by the end of the century under the RCD 8.5, you can see the Northwest Pacific actually showing declining in the uptake by the end of the century. So a green here is meaning this less uptake or more outgassing to the atmosphere. And in fact, one of the significant declines, we start seeing it is the North Pacific intermediate water. So to highlighting the North Pacific intermediate water, I'm showing you here the density, surface density spatial map from the World Ocean Atlas, and here kind of the rectangular showing you the areas that actually when the North Pacific intermediate water is forming. So the North Pacific is originating as a vertical salinity minimum layer around the isobicnal density of 26.2 to 6.4 to 27 in the subsurface, and this is usually occurring east of Japan between the Kuroshio extension and the Ueshio front. So there's the waters that start forming here, and this is actually is playing a vital role because actually it's basically transporting the low salinity and nutrient-rich water from the subarctic to the interior of the North Pacific subtropical gyre, and also to the traveling especially over the North Pacific, and you can see this is also the Northeast Pacific. So it's have actually bigger impact in the interior and what's happening in a bigger scale in the North Pacific. So in this study, we try to use Argo data to estimate oxygen content in the newly formed North Pacific intermediate water and quantify the extent of the oxygen disequilibrium over time and space. And I would like to say this is actually not unique for the North Pacific. Like this paper by Wolf et al. In 2018 in the Labrador Sea, they actually start looking at the convection, and they found when the actually convection is usually is undersaturated when there is like a deeper convection happening. So as you can see here, there's a higher undersaturation associated with deeper convection. But also they noticed a relationship that actually if the convection is ending later in the year, is this more likely to reach or be closer to equilibrium. So why this is important? So actually quantifying the extent of the surface ocean disequilibrium is important because this will improve the studies associated with AOU or apparent oxygen utilization that's helping us to determine the respiration and regenerated nutrients in the ocean interior. So AOU is basically quantifies the oxygen consumption since the water was lost at the surface, and typically we assume that during the convection that the water reaching equilibrium, and this is could cause actually overestimated for the oxygen consumption in the interior ocean, and can have like other influences when you're actually looking at, for example, the carbon cycle or biogeochemical processes. So we looked at 16 floats, and this is showing all the floats that we actually so far focusing on in the Northwest Pacific. This is showing you the trajectory of all floats. I'm not going to focus on all of them. I'm just going to choose this float here. And this is the trajectory of the float. And you can see it was actually going through different water masses. You can just see going from 45 to almost like 32 degree north. So this is kind of like traveling in the different water masses there. And here I'm showing you the cross sections for the entire float. So you can see here the black here, this is actually in the upper 500 meters of the ocean, and the black line here showing you the mixed layer, and this is things in gray here is actually the isobicnal dips. So the upper one is 26.2 and the lower one 26.6. So when you have this is kind of like overlapping with the mixed layer, this means we are kind of like in the North Pacific intermediate water. You can think about it in this way. So you can see here there is kind of like 3 cycles in this float for the mixed, when the mixed layer getting deepening in the ocean. So it's basically it's warm and it starts cooling down, and then the mixed layer is deepening and real stratification happening again. And this is usually happening in the winter in March or like late March, early April, and then we can go to the second year and the cycle start repeating. So you can see this is recycling, and you can see there is inter-annual variability. It's not like the same each year. There's like differences from year to another. And if you start looking actually at the time series, so for example here, if you here is a mixed layer dips that I showed in the previous slide, and I start looking at the time series of different layers. So 10 meters, 100, 150, 200, etc., and until 400 meter. You can see when actually it's deepening, you can see as we expected, the waters will mix, so the temperature will be kind of like similar from the surface to the deepest layer, which is 300 meter here, or even 400 meters. So you can see it's kind of like close, and you can see this in all mixed layer and in the other 2 cycles too. Looking at the oxygen concentration, I know this color here is not like making good justice for this plot, but you can see here there's kind of like oversaturation, and it starts kind of like really there is uptake when the water is actually like the mixed layer is deepening and then is going again, and there is kind of like oversaturation or outgassing to the atmosphere. So this kind of, and you can see this is occurring when the mixed layer is oversaturation going down, and there is kind of like uptake, and then it's happening again. There is super saturation or outgassing.
Mohammed, you have 1 minute left.
Sure, thanks. And here it's showing you the layers between the time series between the layers, also for the oxygen concentration. And you can see here, if I draw a line at 100, I just want to highlight it's not really reaching 100%. There's no actually here when the cycle is not reaching 100% when the mixed layer starts shallowing again. And to show this even a little bit in good way, I'm just focusing on this cycle here. And you can see in blue here is oxygen saturation, and in red is the temperature. And you can see in the beginning of the cycle, there is kind of like oversaturation due to bio or water mixing. And then there is outgassing happening. And this is followed by uptake before the convection. So this is kind of like the water start cooling down, start getting ready for deepening the mixed layer. And there is also uptake happening during the mixed layer during the convection itself. And then there's re-stratification. The water start warming up and the mixed layer is shallow. And at the end, again, you can see the cycle is repeating itself. So quickly here, this is if you look at the evolution of the oxygen saturation during the convection. So I'm just focusing only on when it was happening during the convection. So here, 26.2 to 26.4, this is when the North Pacific Intermediate water. And if you start looking at the oxygen saturation in the upper 400 meter, you can see it's never actually going beyond 100. It's always in the left of this kind of dashed line. So this is usually undersaturated. And we found this is actually phenomena that exists in many of the floats, and usually we estimated around 2% to 8%. And by that, I'm going back again to my first slide. So this is, so this is the undersaturation calculated by 2 to 8% at the end of the convection. And we're still working on this to quantify this more by doing more rigorous analysis on these floats. And thanks for listening, and I'm happy to take any question if you have any time.
Thank you. Are there any questions? Oh, yes, Jinyu.
Hi, very nice talk. And so, Mohammed, you mentioned this is an area which is a strong convection, and you argue the physical process played an important role for the disruption. But is that really true for other regions? My question is how important role of the biological process?
Yeah, this is really good question. Like, yeah, it's playing a role because if you have biological process causing oversaturation in the water, so it's playing role in terms of like impacting the oxygen saturation and the oxygen concentration in the water. So so it's usually we see this when actually after the mixed layer is kind of shallow. So it's just bringing these nutrients back to the surface from the deep layers, and then start like regenerating this kind of like phytoplankton blooms again, that's causing this saturation at the end of this kind of like the cycle.
Yeah, I have another question is if over the area, which is the temperature salinity kind of uniform during the winter convection period, how did you calculate mixing their depths?
How you calculate the mixing of the depths?
How did you calculate mixed layer depths in the winter time, have a strong convection, which is the temperature salinity are uniform in the top, let's say, I don't know, 500 meters?
Yeah, so actually there is like this established kind of equations we can use as a threshold. So in this case, I use a density threshold. So you can, there's like papers by, for example, Horte et al. In 2009, they actually using specific methods to calculating the mixed layer depth. So I followed the same exact method. And in this case, usually people using density or temperature to as a way to actually define the mixed layer depths. And for this example, I used, there's many ways of doing it. I use the density, and you need to do double check again to make sure it's actually makes sense. That's your calculation for the mixed layer depths. Yeah.
Yeah. Thank you, Muhammad.
No worries. Thanks for the questions.
Thank you. And I invite people to continue posing the questions in the chat so that we can move to the last talk of the session by Inge Deschepper about exploring the forcing behind the productivity of the Hudson Bay complex.
Great. Can you see my screen? Perfect.
Yes.
Okay, thank you very much, Cedric. Hello, everybody. I'm Inge Deschepper, and I am a PhD candidate at Université Laval under the supervision of Frederic Maps. And I'll be talking a bit about the productivity of the Hudson Bay complex. Now, the Hudson Bay complex is located just south of the Canadian Arctic archipelago. So it has a classification of a subarctic system. And what is meant by subarctic system is that it experiences seasonal ice cover, so fully ice covered in winter and open water in summer. And the sea ice dynamics has an impact on the productivity that in the late winter and early spring, you have the presence of a polynya in the northwest of the bay, and the sea ice flows and usually follows the general circulation of the Hudson Bay, where the sea ice is pushed and piles up in the south and the southeast of the Hudson Bay. The Hudson Bay is also highly impacted by a large amount of rivers that discharge into the Hudson Bay, providing nutrients that can stimulate productivity. Now, how much each physical forcing impacts the productivity of the bay can be assessed by using models. And we ran two models using the NEMO 3.6 and a 4 configuration that has a sea ice model coupled to it, as well as a biogeochemical model called BLING. But both the two different models have two different atmospheric forcings based on bias-corrected CMOS scenarios, MIROC 5 and MRI. Both models also have regulation regulated river runoff provided from a hydrological model called HYPE that was run also using the corresponding atmospheric forcings. Now, before we go into the analysis, we want to try and validate the model a little bit to make sure that what we're actually seeing in the model actually makes sense. So we did point comparisons with observations taken in 2018 during the BASIS cruise that was on the Amundsen research vessel. And there were multiple different observations taken. And we did these point comparisons at the black dots that you can see. I'll only be talking about the phosphate because phosphate is the currency of the model. And we got a correlation coefficient between 0.41 and 0.51, which isn't great, but it isn't horribly terrible either. And then we also did a comparison with the 8-day average chlorophyll data from the Modus Aquis data, and we also got about a 0.43 to a 0.46 correlation coefficient. And some of the reasons why this may occur is hopefully can be explained by the video on the right. So in the top of the video, you have the two models runs on the top showing chlorophyll concentrations, with the white being a mask of 10% or more ice cover. At the bottom, you've got the Modus Aquis 8-day average satellite data. So one thing you'll notice as the video plays is that the Modus Aquis data actually shows that the sea ice retreats quite earlier than the model data, as well as the sea ice forms a month earlier than the model data. This can explain that there is a time offset with doing exact point comparisons this way. But if I replay this video, at least the patterns of the sea ice retreat, as well as reformation from retreat from west to east, follows what's seen in the satellite observations, as well as the freeze up is similar, as well as when you have maximum chlorophyll production just off downstream of the rivers, as well as of downstream of Belcher Islands. It's also seen in the models. So our model is actually not doing too badly. Now, when we try and look at what forcings are actually impacting the production within the model, we used empirical orthogonal functions. This is a great tool using principal component analysis. And I'm quickly going to take a little bit of time just to explain how to interpret Eofs. So you have two parts of an Eof. You've got the mode that explains the percentage of spatial distribution related to a principal component. And then you have a principal component, which explains the time series variability explained by the mode. And usually how you interpret it is you take a peak, let's say for the peak within the time series, and you multiply it by the principal component by the mode. And then that would be your productivity within at that point in time. But you can also have a negative productivity. If you multiply a negative PC by a positive mode, that means there's a negative production in that area. Now, when we actually go into looking into the Eofs, Eof 1 shows about 54 to 48% of the variability, and this is definitely due to the seasonal nutrient and light limitations that we put into the model. And what's good to see that we're seeing a two-peak bloom occurring in the Hudson Bay because it is a subarctic system, which is a plus point for the model. Woohoo, it's doing what we want it to do. It gets more interesting when we look at Eof 2. Eof 2, you start seeing a bimodal pattern where you have positives and negatives even in the mode. And we were able to match the Eof 2 to the mixed layer depth dynamics that occurs within the Hudson Bay complex. And the Eof 2 explains about 14 to 18% of the variability. And what's interesting is that you have positive production when the mixed layer depth shoals downstream of the rivers, as well as off the downstream of the Belcher Islands in both models. when we start looking at EOF3, 8 to 13% of the variability in the chlorophyll production is driven by river runoff. And as the river runoff starts with the spring freshet, you get positive production, particularly in James Bay area, with very high river runoff in both areas, which is quite interesting. And then when we look at EOF4, it explains around about 7% of the variability, and we were able to match it with the sea ice production, not only because of the time series comparison, but also with the mode pattern that's seen with the west and the east pattern. So if you have the start of the sea ice melt in the reduction and production, you have positive production occurring on the east, and then once it fully melts and enters, and you have production switching and occurring more on the east, which is a great thing to see. So in conclusion, the model captures the spatial variability of production. And it's not great in point comparisons, but when we look at the satellite comparisons, we are capturing some of the main features. And the main physical forcings that explain the variability that's happening in the Bling model is the seasonal cycles associated with nutrients and light, which is a given, it's part of the model. The shoaling and sinking of the mixed layer depth, then the river runoff, and then the sea ice production. And this is understanding of the physics forcings and how it impacts the production helps us with interpreting future predictions, as well as if there's any events that occur, how much or the percentage of the variability in that in the production will be impacted. So let's say there's a extreme drought that occurs and reduces the amount of river runoff that is coming into the Hudson Bay complex. This will have an impact of 8 to 13% on the production within the Hudson Bay. Thank you very much, and I thank all the funding sources as well as the computational support that I received to be able to do these results. I think I'm still in time. If anybody has any questions, thank you very much. I'm going to stop the screen share.
Thank you, Inga. I might have one question. Thanks for your really interesting presentation. When you compare satellite chlorophyll data, I presume, with the model data, what transfer function are you using? What value do you extract? Just surface, or you integrate over some optical depth, which is variable or not?
Yeah, so we chose to integrate over the top 10 meters. It was advised by a group at Rimouski, actually. I forgot his name now. Sorry. But because it is that thing of closer to the river plumes, you don't have as much optical depth. But for the rest of the bay, that we decided to do a 10-meter weighted average for the model comparison.
So that's a choice you made based on raw knowledge, but how sensitive your results are compared to that specific method you use for intercomparison. So that's maybe an open question, but have you thought about it?
Yeah, that's a very open question, and I'll definitely have to look into that sensitivity to it. But yes, thank you very much.
Thank you.
There's a question from Natasha Ridenor in the chat. Natasha, do you want to ask it, or should I read it?
I can try. My kids are sleeping, so hopefully they don't wake up by this. But that was a great talk, Inga. I just wanted, so your EOF2, it's on your mixed layer depth, but that would, I imagine, sea ice coverage would also be related to that, right? So how did you differentiate the mixed layer depth from the sea ice coverage, if that question makes sense?
It's one of the things that I was thinking as well, is that it's the mixed layer depth is definitely dependent on the dynamics of the sea ice, because if you have wind, the sea ice prevents the wind shear and more mixing occurring. So you when there's sea ice cover, you've got a deeper mixed layer depth, and then when there's no sea ice, you've got a you can have that shoaling occurring. So it's definitely the dynamics of the mixed layer depth is linked to the sea ice extent, or concentration that's there. But EOF4 is linked to the sea ice production. So when it grows or melts, so it's slightly different dynamics, but it's still very linked. Yes.
Okay, are there any other questions? Well, if not, that ends our session. And I want to thank all the presenters for the great presentations and discussions. And I would like to remind everybody to go and see the poster by Greg Sutherland during the poster session tomorrow. Thank you.
Hi, everyone.
Thank you very much.
Thank you.
Thank you. Have a good day.